Okay, so hypergeometric, just a fancy word, okay? So now it's the opposite of binomial. So binomial was independent trials. Okay, so again, we're looking at multiple trials. So this one would be, binomial is independent, this one is dependent. Okay, binomial had replacement, this one does not have replacement. Okay, so like the deck of cards, we take a card out, we don't put it back now. Okay, so non-replacement. Still looking at success and failure, a different formula now. Okay, it looks weird here, but it's like 7 choose 2 times 5 choose 3 over 12 choose 5. Okay, I'll explain how to do it with examples. The expectation is still the same. Okay, it's still n times p. Okay, in the book they give you a different one. Don't worry about that one. Yes.
For the letters in this formula, are they the same? Like, do they have the same meaning as the ones in 4.3?
Yeah. So yeah, I should have broken those out, right? So no, they're the same. Okay, so n is still your total. So n is still your total number of trials. Okay, r is now your successful trials. We'll go through the example. It's a little bit different. Okay, let's go through number 1. Okay, on a team of 15 astronauts, 6 are women and 9 are men. If 4 astronauts are selected at random, what is the probability that 2 men and 2 women are selected? So we've done questions just like this already. We've done this in chapter 3. Okay, now we're just doing probability now. So in chapter 3 we did the number of ways it can occur. Okay, so we did something like this, for sure we did. So let me see, we just changed it to probability now. Before it was just the number of ways, now it's probability. So how many ways can this occur? So I want to choose 10 men and 10 women. Sorry, 2 men and 2 women. Okay, so let's do the men first. How many men do we have in total? We have 9. So we want, there's 9 males and we're choosing how many? 2. And then here comes the and. And tells you to multiply. Okay, that was the men. Now the women. So how many women do we have? 6. And we're choosing 2 of them as well. Okay, so we did something like this in chapter 3. So the number of ways that occur. Now we want the probability. Actually, we did probability. No, we did this in chapter 3 as well. Now the bottom is the total number of ways it can occur. Okay, so it's the total. So this is the way you could, this is an easy way to check. It's 9 plus 6. So add these 2 together, and then add these 2 together. So 9 and 6 is 15, so there's 15 people in total. And you're choosing 2 plus 2 is 4. I don't really explain the formula that much because it kind of looks all confusing. I'd rather just do it in examples and it'll make sense. So males or men, 9 choose 2. Females or women, 6 choose 2. And then this is the total number of ways. So 15 people choose 4. But one thing you could check is that these top ones have to add up to the bottom one. Okay, so 9 and 6 is 15. 2 and 2 is 4. And now we just solve it. You get 0.4 or 40%. So if you look at the formula, so it's A, C, X, and then times N minus A, R minus X. So if you have your total, so 15 choose 4, okay, then we take it from here. So this one was 9 men, so then 15 minus 9, which is N minus A, so 15 minus 9 would give you the 6. And same thing here, so we want 4 people in total. We have 2 men, so this would be 4 minus 2, which gives you 2. It's kind of fusing all the letters, that's why I don't really want to go into it that much. But just know that if you add these 2 together, you get N, add these 2 together, and you get R. It looks really confusing. Okay, next one. Okay, bag contains 10 jelly beans. Oh, by the way, the previous question, why is it hypergeometric and not binomial? Yeah, Sophia?
Because it's dependent. If it was, if 2 men get chosen, then that. I lost it.
Okay. It's the probability change. So as I pick one male, then I'm going to only do one more. So I choose 1 out of, what was it, 9? So 1 out of 9, now I only have, then I have 1 more for the total of 8. Okay, so my total is changing every time I pick somebody. Okay. Or you could say as I pick, so there's 15 people, as I choose 1 person, now I have 14 to choose from. I choose another person, now I have 13 to choose from. Okay, so my total decreases. I don't pick somebody and then put them back into the group, right? I take 1 out. Okay, so 4 blue, 4 green, 2 are red, 4 jelly beans are selected at random. Okay, so this should have said no replacement. Okay, no replacement. So I'm taking jelly beans out, I'm not putting them back. Okay, show the probability distribution for the number of blue jelly beans. Okay, probability distribution, again, represents the chart. I know they kind of get annoying, so we're making a chart. So we picked 4 out. How many blues can I have? What are my possibilities? So there's 10 jelly beans in total. I'm taking 4 out.
4 blue.
I have 4, yes, because I have up to 4. Good.
0.
I have from 0 all the way to 4. Good. So same thing as the boys in the last question. So 0, 1, 2, 3, and 4. So we have 0 blues out of the 10, or if we pick out 4, we could have no blues. We could have 1 blue, 2 blues, 3, or 4. Okay, so that's how it works. So the top, let's do the bottom first if you want to. So how many jelly beans do we have in total? 10, yeah. And how many are we choosing? 4. Okay, so 10 choose 4, that's our total, right? That's the number of ways we could choose 4 out of the 10. Okay, on the top, now we're gonna do the blue times by whatever other color. So if it's choosing 0, so there's 4 blues, and we don't want to choose any of them for the first option. So that means the other 4 jelly beans have to come from the remaining 6. So 6 choose 4. continue it down, so 4 blues, choose 1. And then from the remaining 6, we only want 3 now. All over a 10, choose 4. Now we're going to go to 4, choose 2, 4, choose 3, 4, choose 4. Okay, so the ones I got is 0.07 or 7%, 0.38, 0.43, 0.11, and can you guys confirm this one, 0.005? 99. Yep. Okay, thank you. And then to know these should all add up to about 100% or very, very close to it. I think this is 99.5. So I'll make sure you guys caught up before I continue. Okay, now it says expectation. So calculate the expectation. So that's the E at X. So use the same formula. They do have a different one in the textbook. Just use this. They have like NA over something. So the total number of trials still N. So how many trials? How many did we pull out? How many jelly beans did we pull out? Sophia?
4.
4. Good. Okay, so it's a little bit different than this N here. So it's 4. Okay, so we choose 4 jelly beans. Okay, and then we want the probability that it's going to be blue. So we haven't calculated that yet. You guys should be able to know by looking at the question. What's the probability of picking a blue? If I was just picking one, what would be the probability? Okay. Don't look at this. Don't look at this at all. That's probably distribution. If I reach into the bag, what's my chance of pulling out a blue? Yaba? 40% or 4 out of 10, right? There's 4 jelly beans out of 10. So 40% or 4 over 10, good. Okay, and 40% of 4 is 1.6. So then it says, the next part of that question says, what does it mean? What does that 1.6 mean? percent though, a percent. So what it means is, if you were to pull 4 jelly beans out, you should expect 1.6 blues, which doesn't really make sense, because you can't have 1.6 blues, but on average, you'll have 1.6 blues.
Sounds like when they say you have like 2.3 kids.
Yeah, exactly. Exactly, because it averages it out, right? So out of 4 jelly beans, 1.6 is expected to be blue. So sometimes you'll get 1, sometimes you get 2, but overall the average will be 1.6. So if you pull out 4 jelly beans, 1.6 on average is expected to be blue. So if you pull out 4 jelly beans, 1.6 on average is expected to be blue. Good. Okay, last 2. Okay, in a class of 20 students, 12 have a driver's license. If 6 students are selected at random, what is the probability that at least 2 have their driver's license? Okay, so the key words here. Okay, so whenever you see the at least, yep.
0, 1, 2. I get to find out that. I don't remember last lesson.
Close, very close. So this is at least 2. Last time it was more than 2. So this is at least 2. So that means we can have 2, 3, 4, 5, or 6. Okay, so there's like 5 options. Okay, so when you get these questions, you just see which way is going to give you the least amount of steps. Okay, so is it easier to calculate 2, 3, 4, 5, and 6, or is it easier to do the total, or 1%, minus 0, 1? Okay, so in this case, it's easier to take the 100% and subtract 0 people with a license and 1 person with a license, as opposed to adding 2, 3, 4, 5, and 6, which will be 5 steps. So we want at least 2, so we're going to say 1, which is the total, 100%. Subtract 0 driver's license. Subtract 1 driver's license. Again, you're selecting 6 from the group. Okay, there's no replacement. I'm taking 6 out of the 20. Okay, that's why it's hypergeometric. Okay, I'm taking 6 from the 20. I'm not choosing 1, putting them back. Taking 1, put it back. Taking 6 students from the 20, so your total changes. Okay, so the first one, so again, we're doing probability, so we need our fraction. Okay, so we're looking at the number 1200 drivers. Okay, so we want to see how many have 0 of them have driver's license. So out of the 12 that do, we don't want any of those. So 12 choose 0. Because we don't want to pick any of the ones with the driver's license. Times. So what's the remaining amount of students? from those 8, we're gonna choose these 6. And all over the total, okay, remember just add these up. 12 and 8 is 20, 0 and 6 is 6. And do the same thing for one driver, for picking one person with the driver's license. So out of the 12, we're gonna choose one of them, and the remaining 6 will choose 5. So my notes here, I have 1 minus 0.0007 minus 0.0173. Which is 0.982 or 98%. So if I had 12 students in the classroom out of 20, and I selected 6 students, 98% chance that 2 or more will have a driver's license. Okay, now the last one, how many should we expect? So N represents our trials, which is 6 trials here, because we're taking out 6 students. Okay, and what's the probability of the people with the license, So probability is 12 out of 20, or 60%. So 6 students, the probability of having a person with a license is 12 out of 20. From my notes, 3.6. So on average, if I were to pick 6 students from the class of 20, 3.6 of them will have a license. How many people have license here? 1, 2, 3?
Oh, real license, like you can drive by yourself?
Oh, G2.
Oh, yeah, I don't know that.
No.
COVID ruined that for me.
Oh, really, eh?
I have to wait till December.
I waited
December.
7 months.
Oh,
to
you
get
went
my
July
July.
or June.
Yeah.
Oh. Sorry?
I still have mine yet.
You did
I
G2?
Yeah, I got it like a week before or.
No, eh? Lucky you, eh?
I have my test in March.
Yeah, better than December.
When did you get G1 again? It's 15 or 16? 16? And then it's a year or, it's not a rule if you take driving classes.
You have to wait a year if you don't take driving school, and then
And then
driving
it
school
didn't
can knock
even
it down for a couple
I
months.
did.
So like.
Is it 8 months? If you
Yeah.
do
Yeah.
classes, 8 months, right? We're pretty good at that. Or where do you guys go to Orangeville to do your test?
I did.
Yeah.
Driving
Closest
school is the
thing.
most boring thing I've ever had to sit through in my life.
The
All those actual classes?
Yeah, you
Yeah.
keep your camera on and you call Oh, you're at
Oh, it's
Random.
all,
My
okay,
friend says
you
it's,
have to
yeah.
go north.
That's horrible. Oh, it's so brutal.
You'll learn some stuff there.
No, yeah. Like in class.
Alright, last one. This is kind of a weird one. It's kind of a weird one, right? It doesn't fit into anything, right? So I'm gonna try to do it. It's not that difficult. 500 foxes were caught and tagged. I actually saw a fox the on the weekend up north. Later in the year, 80 foxes were caught and 34 had already been tagged. What does it mean to be tagged?
They have no marks.
They have marks, right? So they catch it and they usually, sometimes they put it on the ear. So they'll put a hole in the ear, put a tag there. They do that with fish too, like a dolphin or a shark. They'll cut a hole in the fin and then put a little marker there or a tracking device. Sometimes with animals, they might have the collars. Okay, they'll put a collar around them. Okay, and they get tracked to see their movements and such. Okay, but for tagging, they actually do this. This is real. So they want to see how much the population is. So they maybe in an area they said, well, we want to find out how many deer or foxes there are in this area. That's probably for you. Mr. McKenzie. Yeah. Yep, not a problem. Okay, so they do this, right? I remember I took ecology in university. I took a course and one of the girls used to do deer. So they go out in the area and see how many deers they could tag. So they go look for deers and they tranquilize it and then they put a tag on it, okay? And there's an overabundance of deers in Ontario. So then they go back, so they tag as many as they can, and then they go back to the area, I don't know, another year or another time, and they try to go catch deer again. And they see how many ones they tranquilize, and they see how many have tags already and how many they don't. And from there, they can actually see what the population is. They can estimate the size of the population. Okay, they do this all over the world for different things. It could be rhinos, it could be lions, it could be elephants, whatever it is. They put a tracking device where they tag them. Okay, so we can actually go in and then predict or estimate the population that they have. Because how would they know? They're like, oh, this area has 200,000 deer. Well, how do you know that? Did you actually go out and catch 200,000 deer? No, but they do this stuff. Okay. So this is an estimate. Okay. So we're going to see their estimated population. We're going to do an expectation again. So we're going to do the EX. The expectation is N over P. N times P, sorry. They do with fish a lot too. They say how many fish are in the river. They'll go catch them. Okay, tag them and release them. Okay, let's figure out where there's 3 spots here. So we have the E and X, the N, and the P. So we're gonna figure out where to plug into what. Okay, so P represents a probability. So it's probably the easiest one to come up with. So anything here that gives you a probability. Anything in the information gives you a probability.
Is it 34 out of 500?
Close? 34 out of 80. Good. So 30, you went out, you caught 80, 34 had tags. So we're doing that's going to give us the probability. So 34 out of 80. Okay, so this gives us the probability. And now we want to see, okay, the fifth 500 is either going to go into the E and X or N. Okay? So we got to figure out where we want, where it's going to go. So if we want population, we're looking for the total, right? Which one here represents the total? What represents the total here? The E and X or the N? The N, right? N represents total. Always represents total. So we're looking for N in this case. So that means the 500 is the expectation. Okay, because that's how much we got from the total. So Okay, so now we have to solve for n. So going back to grade 9, might be a little bit rusty on this. How do we solve for n here? So that means we have to cancel out numbers on the right side or move them to the left side.
Move the 500 to where n is and make n equal on the left.
And
That
then
would,
it's decided on the
let's not
right.
cross that way. I don't want to cross that way, it'll make it easier than that. So we have to cancel out the 34 and the 80, so we need to get rid of these. So we have n by itself, right?
Oh, and it's take it to the other side.
Yes? Okay, let's do one by one. What could I move first? I don't want to move the whole thing. Kate?
34.
I'd do the 80 first. Okay, I'll tell you why. So I'll get rid of the fraction. So if I'm dividing by 80 here, divide by 80, what do I do on the other side? Multiply by 80, right? So if you multiply by 80, I do it this way. What I do to one side, I do to the other. So this cancels out. So you multiply 80 on the other side. So 500 times 80 gives you 40,000. So I'm gonna do it right. So 40,000 equals n times 34. So I got rid of the 80. So I divide on one side and multiply on the other side. Okay, now how do I get rid of the 34?
Subtract it from the other side. Oh, divide.
Divide, yes. Why is it divide? Because we are, what are we doing here?
Trying to get n by itself.
Sorry?
Trying to get n by itself.
Yeah, but what operation is this?
Oh, multiply.
Multiply. So when we get rid of it, we have to divide. Okay, so we divide by 34. And I'll show you another way you could have done it. This is probably the harder way, I just realized. So I get 1,176.4, so 1,176 approximately. Put a little dot on the equal sign means approximately. It means I rounded it. I just did it the hard way. I'm so stupid. Sorry, let me just do that one more time. I want to see the easier way. I'll give you guys a minute. Something easier you do. I just made it more. Huh? I made it more complex than that.
Yeah, can you just do 500 times points?
What?
Because 500 times 3 equals 40, whatever, and then divided by 34 equals 1,100.
Yeah, that's what we did. So you could bring it over and multiply by 80, divide by 34. Yes.
I don't know if easier ways.
So what you could have just done, I don't know why I did that way, just divide this first. If I divide it, you get 0.42. And then just divide it over. That's probably easier. So actually solve the brackets, which Ben Mass tells you to do, is solve the brackets. And then, so this is an order. So then divide by 0.425, and you'll get the same answer. So solve this first, and you get 1176. Put the dot on top means approximately, we don't know that it's a 1,176 year, it's just an estimation.